In this set of lectures, we are going to study a very fundamental form of energy, which is the elastic energy stored inside deforming objects. We regard any continuum object as if it is made out of elastic springs, such that once it deforms, there is some sort of a mechanical energy that is stored inside that object. This energy is waiting to be released once the applied loading that caused the deformation is removed. Now, to understand this energy, or to present this energy, we are going to start by one-dimensional systems. A one-dimensional system made out of an elastic spring with a linear relationship between the force and the displacement, which means that the force in the spring is equal to a constant k multiplied by the extension of the spring. And we're going to look at the spring and hang a weight that's equal to mg from the spring. And we're going to try and understand what happens at equilibrium. So, in general, the force in the spring is equal to k multiplied by x. The energy stored, I'm going to call it the potential energy in the spring, or I'm going to call it pi spring. I'll give it the symbol pi in the spring, is equal to the integral of this force multiplied by the displacement. So for any general displacement, when the spring is extended from 0 to x, this potential energy in the spring is given as half kx squared. So this is the force in the spring and the potential energy in the spring at any distance x. Now, what happens at equilibrium? At equilibrium, the external force, mg, will be equal to the force in the spring which is equal to k multiplied by x that corresponds to equilibrium. X that corresponds to equilibrium is then called delta, which is equal to mg over k. Now, to understand what happens to the energy at equilibrium, I'm going to introduce a quantity that I'm going to call the potential energy of the system. The potential energy of the system will be called pi spring, will be made out of two components. First, the potential energy of the energy that corresponds to the energy stored in the spring, minus the work done by the external forces, or you can call it the potential energy lost by external forces during movement. So the potential energy of the system is equal to half kx squared. So if the spring of this point moves downwards a distance x, then the spring has an energy stored that's equal to half kx squared, and the external force mg has lost a potential of mgx. Now, at equilibrium, this is equal to half k delta squared minus mg delta. Now we want to show now what is this quantity at equilibrium. How does this potential energy of the system at equilibrium compares to any other position? So I'm going to take the partial derivative of pi with respect to x. Partial pi with respect to x is equal to 2 over 2 kx minus mg, which is equal to kx minus mg. Now, partial the potential energy with respect to x at equilibrium is equal to 0. So what does this tell me about pi? This tells me the following. If this is x, and if this is the potential energy of the system, at a point of equilibrium, when x equal delta, the rate of change of pi with respect to x is 0, which means that pi, either the potential energy of the system either looks like this or looks like this. And at equilibrium, the potential energy is either minimum or maximum. So how would we know? Calculate the second derivative with respect to x. This is equal to k. This is greater than 0. Therefore, the potential energy is minimum when x is equal to delta, which means that this curve represents the potential energy of the system at any variable x, and when x reaches delta, the potential energy of the system is minimum. The potential energy of the system is minimum when x is equal to delta. Now in the previous derivation, we assumed that the force in the spring, F, which is a function of the spring extension x, we assume that f of x is a linear function of x, which means that we assume that f of x is a linear function of x. It looks like this, and the slope is equal to k. Now the same concept applies whether the spring is linear or nonlinear. If I have a spring that's nonlinear, a spring that as you deform it or as you extend it with the distance x, the force by which the spring pulls is a nonlinear function of x. For example, it's really stiff at the beginning and then it's not very stiff and then becomes stiff again, or it's very stiff at the beginning but then it becomes softer as you start pulling. So for these types of systems, the concept is still the same. Equilibrium is achieved, or in general, the force in the spring is a non-linear function of x, and the energy stored in the spring is equal to the integral of this f of x dx integrated from 0 to x. Now, at equilibrium, the force in the spring is equal to the outside force F. So we're pulling the spring with a force F, and the energy of the system is equal to pi spring minus the work done by the external forces, which is the external force is capital F x. The energy is equal to 0. The energy of the spring is the integral from 0x f of x dx minus f x and so partial pi by partial x will be equal to f of x minus f, which shows that partial pi by partial x at equilibrium you get the equation f of x minus f. At equilibrium, f of x minus f is equal to 0, which means pi is either minimum or maximum at equilibrium. So how would we know? Well, we would take the second derivative of pi with respect to x squared. When you take the second derivative, you find that whether the system is stable or not depends on the sign, or whether the potential energy is minimum or not depends on the sign of the slope of f. So let's go back to the nonlinear springs that we looked at. For the first two, f prime of x, which is the slope of f of x, is always positive, which means both these two curves represent springs that when they reach equilibrium, the potential energy is minimum. Now let's look at the other two curves. This part of the curve is equilibrium. If equilibrium is achieved on this part, then the potential energy is minimum. But if equilibrium is achieved on this downward slope where f prime of x is negative, that means the potential energy of the spring is maximum, and we will show that this is an unstable equilibrium, and we're going to talk about this in a second. And again, here, this is a stable part of the curve, this is an unstable part of the curve, and this is a stable part of the curve. So this area is an instability, or potential energy is maximum at equilibrium because the first derivative of x, or the slope of the curve, is negative. So let's try to understand this with simple examples. If I have a cylinder and a small cylinder that is resting inside of it, if I have a flat surface with a small cylinder that's resting on top of it, and if I have a big cylinder with a small cylinder resting on top of it. Now, in the three cases, I have equilibrium because the sum of forces down are equal to the sum of forces up, is or equal to the reaction, this upper cylinder is fixed, this ground is fixed, this bottom cylinder is fixed, and so these small cylinders are all in equilibrium. The weight is equal to the reaction. The weight is equal to the reaction. The weight is equal to the reaction. Here, the potential energy at equilibrium is minimum. And if I try to move this away from equilibrium, I have to put energy into the system, and so the potential energy of the potential energy at equilibrium is minimum, and so system is stable. Here, at the potential energy at equilibrium is in fact constant. The potential energy does not change if you change the position, and that's what we call system is in neutral equilibrium. And here, potential energy is maximum at equilibrium, and so this is called an unstable equilibrium. The moment the cylinder moves left to the right, it's going to fall, and I'm going to lose the equilibrium. So this is unstable equilibrium. To maintain this equilibrium, I need to input system from outside. I need to input energy from outside the system. So let's look at our curves again and try to understand what stability and instability means when it comes to springs. As we said, these two nonlinear springs are stable. Any descending curve for a linear or a nonlinear spring corresponds to an instability in the system, and the instability can be seen as follows. If I reach equilibrium at a particular point, let's say at x1, if the external force is equal to x1, and if a small perturbation moves, so that's if F is at equilibrium when the spring has moved x1, and this is F of x1, if F is equal to F of x1, and if for whatever reason this point slightly moves to the right, if it slightly moves to the right, so if it slightly moves to the right, then F of x1 will decrease. Since F of x1 will decrease, F will now dominate, and the spring will be pulled in an uncontrollable fashion to the right. So if the spring is being loaded with F, it will be unstable. Let's look at an example. I have a force versus displacement of a nonlinear elastic spring following the above relationship. Now, usually these springs can be used for many applications. For example, there are many small springs with nonlinear force displacement relationship that are used in the for example in the for the applications in lots of biomedical engineering applications. So usually when a manufacturer supplies such springs, it has to tell you the range of applicability of such spring. So I have the force versus relationship is applicable for a range between -5 and 5. So the first thing required is to draw the relationship between the force versus displacement in the full range of applicability of the relationship. So you can just use Mathematica, plot. So first define f is equal to 1,000 x plus 50x squared minus 20x cubed. Plot f when x is between -5 and 5. And you will get this curve, and you should, of course, maybe put some options. The options are to tell me what the axes mean. This is represent. This is x, the displacement in millimeter, and this is the force in Newton in the spring. Find the strain energy stored inside the spring at full extension and at full contraction. The energy is equal to this whole area underneath the graph. So the energy at full extension is equal to the integral of f of x dx from 0 to 5, which, if you want to do it using Mathematica, integrate f x from 0 to 5. The energy at full contraction is equal to 0 from 0 to -5 f of x dx integrate f x from 0 to -5. Now units here, notice the units. This is given in Newton, so the energy is in Newton millimeter. The next question is find the displacement in the spring that corresponds to a force of 3 kilonewton and a force of -1000 kilonewton. So you can find it from the graph. Corresponding to 3 kilonewton is this displacement, and corresponding to -1000 kilonewton is this displacement. And to find the actual number, you need to solve a cubic function, because f, so 3000, which is 3 kilonewton, is equal to 1000x plus 50x squared minus 20x cubed. Find x. X will be equal to 3.121 millimeter. And similarly, -1000 equal to this. Find x. X is equal to -1.084 millimeter. And you can do this by hand, or you can use Mathematica. The best way to find a root of an equation is to say find root f is equal to 3000. Find x, and you have to give me an initial value, for example 0. This will spit out x is equal to 3.121 millimeter. Now, in the last part of the question, it states comment on the behavior of the spring at x equal -33.33 and x equal 5. So at x equal 5, you're going to find that this is unstable under the force control because the slope of how the force changes with respect to the displacement is 0, which means right here and right here at x equal 5 and at x equal negative 3.33, the spring is unstable under force control. It's okay to use it to under displacement control where you're controlling the displacement of the spring, but if you're at this point and you're trying to apply a load on the spring will become unstable. The spring will become unstable and will extend beyond its limits. So there are different kinds of energies, and the type of energy that we're interested in here is the linear elastic energy, or the energy stored in a linear elastic spring, or in a linear elastic continuum, which looking at the continuum as if it is a spring. Now, you need to realize that there are other types of energies stored in or used in the deformation of objects, and these are nonlinear or non-elastic springs. For example, when you're dealing with plastic materials, where when you apply a certain deformation to that material or to that spring, and then after you remove the load, the spring does not go back to its original position. The spring does not go back to this original position means you applied a certain energy, and then when you try to take it back from that spring, the spring kept some energy to itself, and that energy was used to change the structure of the spring itself, the internal structure. Maybe it was also used for some heating of that structure, or changing of the structure, or changing the internal structure of the spring. And so you end up with a stress strain curve or force displacement curve of the spring that looks like this. As it's being loaded, you're storing energy inside, and when you unload it, but you don't go back to its original position, and there is a plastic or some deformation inside the spring that corresponds to some damage that occurred, or some change of the structure of the spring. Also, if I have the type of energy that we described so far is potential energy of a system when I load the spring from when I slowly load the spring. So if I have a spring and I slowly apply load mg, very slowly without considering any dynamic effects, and so the type of energy that's stored in the system is simply potential energy. However, if I apply the load or the mg on the spring that's resting at x equals 0, and I apply the force in a sudden way, then in order to find the position of the spring, I need to solve a differential equation that looks like this. The force acting downwards is mg, the force acting upwards is kx, and this will cause the mass, the force acting downwards will cause the mass to move with an acceleration x double dot. And so what is x? As a function of time, you're going to find that if I do something like this, if I apply the force in a sudden dynamic way, you're going to find that if the static equilibrium is delta, then the spring will vibrate, or the load will vibrate around the equilibrium position. X will have a function that's equal to mg over k. The solution to this is mg over k, y minus cosine square root of k over m multiplied by t, where t is the time. At any at any instant in time, I will know where x is, and I will know where the position of that point is, the extension of the spring. And notice that the maximum x occurs when cosine square root of k t over m is equal to 1, is equal to -1, which means that the maximum x is equal to 2 mg over k, which is equal to 2 delta. So what does this mean? Now this is very important for the design of structures that has some dynamic load application. For example, if I have a bridge and the cars appear or come onto the bridge, there is a dynamic effect that depends on the length of the bridge. Because if the bridge is short, then the dynamic effect of the cars is higher, because the time for which the car reaches the middle of the bridge is really fast, so it's almost equivalent to saying that the weight all of a sudden appears on the middle of the bridge. For longer bridges, it can be considered as more like a static state, because it takes the car a really long time to approach the middle of the bridge, which is equivalent to saying that I'm really applying the load very slowly. And for the design of such bridges, I have to apply some dynamic effects or some dynamic factors. And as you can see here, the maximum effect that I can get is twice. And that's why the maximum dynamic effect factor is equal to 2. And depending on the length of the bridge, you'll find that the dynamic effect factor will be less than 2. The potential energy of the system in this case is equal to half kx squared minus mgx. The kinetic energy of the system is equal to half mv squared. The total energy of the system is equal to the potential energy plus the kinetic energy, half kx squared minus mgx plus half mx dot squared. Now what you will notice is that the energy stays constant. When you take the partial energy by partial t, you get this equation, which is equal to the velocity minus the equilibrium multiplied by the equilibrium, the dynamic equilibrium equation. And thus, total energy of the system is equal to 0. Okay, so these are different forms of the energies stored inside objects, or in one-dimensional objects. And what we're interested in for the rest of this chapter is energy inside a continuum. Now, how can I relate this to a continuum? In a continuum, the energy can be looked at as if we have the following. If I have a small cube and I apply force F and it extends a distance dx, then the energy per unit volume will be equal to F multiplied by dx divided by A multiplied by the length. This is the area and this is the length. F over A, I can call it the stress. dx over L, I can say that this is so F over A is the stress, dx over L is the strain. So the energy per unit volume of a continuum is in fact equal to sigma on 1 d epsilon on 1 plus sigma 2 2 d epsilon 2 2 plus and so on. So plus sigma 1 2 d epsilon 1 2 plus sigma 2 1 d epsilon 2 1 plus and so on, which is 9 components obtained by the sum from I and j equal 1 to 3 sigma ij d epsilon ij. So we're not going to cover these sections for the derivation of why the energy is equal to this. We're just going to agree that using this very small analogy, that the energy per unit volume is equal to the stress multiplied by d epsilon 1 1. Now, what happens if I have a particular type of material which is linear elastic material? For a linear elastic material, I have a very specific type of energy. In linear elastic materials, I know that stress and the strain, this is sigma on 1 and this is epsilon on 1. If this is sigma on 1 and this is epsilon on 1, I know that there is a linear relationship between them. So the energy at any point, if this is sigma and this is epsilon, then the energy per unit volume is equal to the integral of sigma on 1 d epsilon on 1, which is equal to sigma on 1 epsilon on 1 over 2. And so the strain energy in linear elastic materials in small deformations, because I'm going to use the small deformations because I'm going to use the small strain matrix, is equal to half multiplied by sigma on 1 epsilon on 1 plus sigma 2 2 epsilon 2 2 plus and so on sigma 1 2 epsilon 1 2 plus sigma 2 1 epsilon 2 1 plus and so on. 9 components. But in the previous chapter, we already know that I can replace sigma on 1 as, or in general, the stresses is a function of the strains for linear elastic isotropic materials, and in fact I can also replace the strains with a function of the stresses. So if I replace the strains or the stresses with each other, I reach the following two very important forms for linear elastic isotropic materials. I can write the strain or the strain energy per unit volume as a function of the strains, or I can write the strain energy as a function of the stresses. And for these, mu is equal to G, which is equal to E divided by 2, 1 plus Poisson's ratio. And for this, lambda is equal to this is Lemi's constant, and you can check it in your in the previous chapter, and it's equal to E multiplied by Poisson's ratio divided by 1 plus Poisson's ratio 1 minus 2 Poisson's ratio. Now in the chapter 2 we introduced the hydrostatic stress and we introduced the deviatoric stress. We said that the stress can be decomposed into a matrix that's called P 0 0 0 P 0 0 0 P, where P is the hydrostatic stress, plus sigma 1 1 minus P, sigma 1 2, sigma 1 3, and so on. And we call this the deviatoric stress tensor, and this is the hydrostatic stress component. And this was done because for linear elastic isotropic materials, I can always, or I can assume, that this part of the stress is responsible for volume changes or volumetric changes in the material, and this part of the stress is responsible for change of shape. So this part of the stress is responsible for shape changes, which means if this is the cube, the distortion of the cube is caused by the deviatoric stress tensor. Now to see this, we are going to look at what happens to the strain, or we're going to look at the volumetric strain. The volumetric strain, you'll find, is equal to, or as we studied in the strain chapter, is equal to epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. From the constitutive law chapter, we studied that epsilon 1 is equal to sigma 1 1 over E minus Poisson's ratio sigma 1 1 sigma 2 2 plus sigma 3 3 over E. So this is epsilon 1, epsilon 2 2, and so on. When you perform this calculation, you find that epsilon 1 plus epsilon 2 2 plus epsilon 3 3 is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3 over E multiplied by 1 minus 2 Poisson's ratio, which is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3. Remember that P is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3, the average. So this is equal to 3P multiplied by 1 minus 2 Poisson's ratio over E, which tells me that the change in volume, delta V over V, happens only if I have P. That P and the volumetric strain are related. So P, volumetric strain, is directly proportional to the hydrostatic stress P. Now, utilizing this fact and utilizing the strain energy equation, we can further decompose the strain energy into two components. We know that the strain energy is equal to 1 over 2 sigma 1 1 epsilon 1 1 plus sigma 1 2 2 epsilon 2 2 plus, and so on. for linear, elastic, isotropic materials, we can show that U can be written as follows. When you replace the strains with the stresses, you can show that U is equal to a volumetric component plus a deviatoric component. The volumetric component is dependent only on trace sigma, which is 3p, and the deviatoric component is function of the von Mises stress, which shows the von Mises stress is actually responsible for the change of shape. So let's introduce a few examples. If the state of stress in a linear elastic isotropic material is given by the following stress matrix, find the strain energy density, deviatoric and volumetric components stored in the material. Now, it's very important to know whether are we talking about a linear elastic material or linear elastic isotropic. Because if it's a linear elastic material, in general, the strain energy is equal to half sigma 1 epsilon 1 plus sigma 2 epsilon 2 and so on. But once I said isotropic, I have forms. I can replace epsilon with the stresses, so I can utilize the form that says that the strain energy in a linear elastic isotropic material, as I'm scrolling up, is function of the strains or the stresses, so I can utilize this form. Function of stresses from above, or I can maybe write it again here. This is equal to 1 plus Poisson's ratio over E, sigma 1 squared plus sigma 2 squared plus sigma 3 squared plus 2 sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus and this will be equal to 0.155. The energy is obtained by multiplying the stresses by the strains. So this is mega Newton meter, and this is per volume, so per meter cubed. The deviatoric component is equal to 1 over 12g multiplied by the von Mises stress squared. And we already know how to calculate the von Mises stress. This will be equal to 0.138 mega Newton meter per meter cubed. And the volumetric will be equal to 1 minus 2 Poisson's ratio over 6e multiplied by sigma 1 plus sigma 2 plus sigma 3 squared, and this will be equal to 0.016 mega Newton per meter cubed, and you can verify that the sum is equal to the total. All right, the next question, the next problem, we have the strains in a linear elastic orthotropic material. Now, it's an orthotropic material, which means I can only utilize the general form. So I'm going to go up. All these are functions of Young's modulus and Poisson's ratio. These are all for linear elastic isotropic materials. The only general form is this. General form. General form for linear elastic materials. So, a linear elastic orthotropic material are given by this strain matrix. And the material acts as orthotropy aligned with the orthonormal bases used. So, this is E1, E2, and E3. And the relationship between the stresses and the strains are given in this orthonormal basis set. And we need to find the strain energy. And we're given the 3 Young's moduli, the 3 Poisson's ratios, and the 3 G's. So, first, the energy is equal to 1 over half, 1 over 2, sigma on 1, epsilon on 1, plus sigma 2, 2, epsilon 2, 2, and so on. 9 components. So I need to find the stresses. I know that epsilon on 1 is equal to sigma on 1 over E11 minus sigma 2, 2 over E22 minus Poisson's ratio 3,1 sigma 3,3 over E. So this is from orthotropic stress strain relationships. So we can solve the stress strain relationship to find sigma on 1, sigma 2, 2, and sigma 3, 3, which you will find to be equal to, you'll find that the stress matrix finally will be equal to 1, 1.05, 0.07, 1.05, negative 2, 0.14, 0.07, 0.14, 0.2 units of MPa, and U, which is equal to half each component multiplied by the corresponding strain component, 1 over 2, the sum from I j equal 1 to 3 sigma ij epsilon ij. This will be equal to finally 0.0412 meganewton meter per meter cubed. The final problem in the energy section is for a plate that deforms in a nonlinear fashion. The position function in the dimensions of meter of a plate follows the following form. So I have a plate has dimensions 2 and 1. So the plate looks like this, and the position function is according to these functions, and the material is linear elastic with Young's modulus of 210, and Poisson's ratio is 0.3. Now, the strain energy, because the stresses and the strains are different at every point on the plate, the energy per unit volume is also different at every point in the plate. So we need to find the expression for the strain energy density as a function of the position inside the plate, and we need to draw the contour plot of that strain energy. Now, you can regard a plate like this as if it's a spring, and under this deformation it has been loaded, and there is an energy stored inside that loaded continuum, which is, you can view it as a spring, a 3-dimensional spring. So we need to find the total energy, which is the integral of the energy per unit volume integrated over the volume. Because every point there is some energy stored inside of it, the total energy is the integral of that energy. And we need to find the expressions for the deviatoric and the volumetric strain energy density functions and draw the contour plots of these on the plate. So what we have is the position function. So the first thing we need to do is the displacement to find is the displacement function, which is the old position, the new position minus the old position. The new position minus the old position, you will get the following form: 0.001 x2 plus 0.0002 x1 squared. That's the first component of the displacement. The second component of the displacement is equal to 0.001 x2 minus 0.0002 x2 squared. So this is the vector of displacement of the plate, every point in the plate. The strain is equal to the gradient of u, the gradient of u matrix is equal to partial ui by partial xj, as we studied in chapter 3, chapter 3. And the strain, the engineering or the small strain matrix, is equal to half the gradient of u plus the transpose of the gradient of u. And as expected, the strain is a function of the position. It's different at different points along the plate. So this is the strain matrix, and the next thing is, what is the stress? Because we need to find the energy, so we need to find the stresses. Now, to find the stresses, we need to convert or use the vector representation of the strain, which was given as epsilon 1, epsilon 2, 2, epsilon 3, 3, 2 epsilon 1, 2, and don't forget the 2, 2 epsilon 1, 3, 2 epsilon 2, 3. And this is equal to a matrix multiplied by sigma 1, 1, sigma 2, 2, sigma 3, 3, sigma 1, 2, sigma 1, 3, sigma 2, 3. This is a 6 by 6 matrix. By inverting this 6 by 6 matrix or finding the other matrix when multiplied by the strain that gives you the stress, you are able to find 6 values for the stresses, which will be functions of the position because the stress varies as the strain, and so the final stresses will look like this. One to 1.154 plus 113.077 x1 minus 48.4615 x2, and 5 other components, 1, 2, 3, 4, 5, 6 in units of MPa, and the energy will be equal to half each component multiplied by the corresponding component. A huge function of position. Now the total energy will be equal to the integral of u on the volume. This is the energy per unit volume at every point. We can integrate u. First, dx1, dx2, dx3. dx3 is according to the thickness of the plate from 0 to t. dx1 is from 0 to 2, and dx2 is from 0 to 1. And the number here will be equal to 0 0.04 meganewton per meter. And of course, it's not meganewton meter, and it's no longer per meter cubed because we have integrated along the volume. The deviatoric strain energy will be equal to 1 over 12 G von Mises stress, which will be equal to function of x1 and x2. And the volumetric strain as well will be equal to 1 minus 2 nu over E multiplied by sigma 1 plus sigma 2 sigma 3 squared, which will be another function of the position. And you can plot these functions as I will show you in the Mathematica tutorial that will follow this chapter. For beams, we can look at the linear elastic energy, or the linear elastic strain energy in beams. We can write it in terms of the forces that we or the internal forces that we use for the beam. The total strain energy, as we showed in the previous example, is the integral of this energy integrated over the volume of the beam. So the total strain energy is equal to the integral of sigma ij, or sigma ij d epsilon ij, multiplied by the integrated over the volume. The volume is dA multiplied by dL, or dx. Now remember, in beams, Euler-Bernoulli beams, we assumed that the only non-zero strain component was epsilon 1, and we ignored Poisson's ratio effect. And we assumed that epsilon 2 is equal to 0. And so the energy is only obtained by multiplying sigma 1 multiplied by epsilon 1 over 2, because it's linear elastic. Now, utilizing the relationship between the stress and the strain and the bending moment diagram, as remember that sigma 1 when you revise beams chapter, sigma 1 was equal to negative m x2 over I. And there was another relationship between epsilon 1 and sigma 1, and the second derivative of y with respect to second derivative of y with respect to x1. So if you use all these formulas, you realize that the total energy can be written in terms of the bending moment and the second derivative of y integrated over the whole length of the beam from 0 to L, which, since we know that m is equal to EI d2y by dx1 squared, you can replace d2y by dx1 squared with m, or you can replace m with d2y by dx1 squared. So you get three equivalent forms. The first form is 1 over 2 m multiplied by d2y by dx1 squared. The other form is m squared over 2ei, and the third form is d2y by dx1 squared multiplied by ei. Well, of course, the three are equivalent. You just have to choose whichever you're more comfortable with to calculate your total strain energy inside a beam. The one thing is, you need to realize that the energy is always given as the integral of a measure of the stress. In this case, we have the moment, and a measure of the strain, and in this case, it's the second derivative of y with respect to x1 squared, which comes from sigma 1 and epsilon 1. So, for example, we have a linear elastic small deformations cantilever beam. we need to find an expression for the strain energy per unit volume as a function of the position, P, and the beam length. And we need to find the total strain energy stored, assuming Young's modulus to be E, and that the beam has a rectangular cross-section with a moment of inertia I. So, to find the we know the displacement of the beam. We know that the equilibrium equation is EI d4y by dx1 power 4 is equal to q, which is 0 in this case. And if you solve and you find your boundary conditions is y equals 0 and theta equals 0, and here the shear is equal to p and the moment is equal to 0, you solve this equation and you find that the moment along this beam is equal to negative p multiplied by L minus x1. And the stress at any point is equal to negative m x2 over EI, which is equal to negative p L minus x1 x2 over EI. So if this is the beam, x2 and x1, sigma on 1 at every point is given by this equation. And epsilon on 1, you can just say it's equal to sigma on 1 over E, which is equal to, negative mx2 over I. So epsilon 1 will be equal to negative p L minus x1 multiplied by x2 over EI. So the strain energy per unit volume is equal to half sigma on 1 epsilon on 1 over, which will be equal to p squared L minus x1 squared x2 squared divided by 2 EI squared. The total strain energy in the beam, the amount of energy needed to deform that beam, is equal to the integral of that energy on the volume, or is equal to the integral of m d2y by dx1 squared 1 over 2 dx1 from 0 to L. Whichever you want to use, I will utilize this form. And when you do the integration, you'll find the value to be equal to p squared L cubed divided by 6EI. Now notice that this energy is equivalent to the energy supplied. This is equivalent to energy supplied by external load through the gradual displacement of the beam. Since the beam is under this P and this delta, if you do the calculation, will be equal to PL cubed over 3 EI, the external energy is equal to P multiplied by delta over 2, which is equal to P squared L cubed divided by 6 EI. And so the strain energy in the beam is equal to the energy supplied by the external forces, P squared L cubed over 6 EI. So this is it for the energy portions. Section 7.3.4 and point 3, point 5 are not covered in these in the course. And in the next lectures, we're going to study the principle of virtual work as an introduction to numerical methods to solve the differential equation of equilibrium.